Welcome everybody. I am really excited to be here with you at GitHub Universe and share a little bit about how the open source quantum community develops with Codespaces. But first, hi, I'm Dr. Sarah Kaiser. I'm a senior cloud developer advocate at Microsoft and a QIR Alliance core maintainer. I've been a research Pythonista for over 10 years now, working on all kinds of different cool cutting-edge technologies. Everything from using Jupyter notebooks to control satellite optics to building VR hardware. And what we'll be talking about today is quantum technologies. Here's my really quick, obligatory one-slide explanation of quantum computing. Quantum computers are hardware accelerators. You're probably familiar with other types of hardware accelerators like GPUs or graphical processing units. And these are basically specialized pieces of hardware that you can use to accelerate or maybe evaluate parts of programs that would be otherwise kind of hard. And as we know from kind of how we've integrated GPUs into our software stack, we need some specialized tooling to kind of connect users writing in high-level languages like Python all the way down to actually leveraging that hardware. When I'm writing in Python, I'm not directly thinking of the instructions available on my GPU. So that kind of stack is really important. But now you know what a quantum computer is. Let's talk. Building quantum tech is hard. Whenever I tell somebody what I work on, this is usually the first thing that we talk about, and is part of the reason that I actually got started in the field in the first place. Somebody said it was really hard, and I said, okay, try me. But having worked in the field for quite some time now, I really don't think it has to be. And what I want to show you in my talk today is how the QIR Alliance, which is part of the quantum open source community, uses tools like Codespaces and VS Code to reduce some of those barriers and make developing the quantum stack easier and just a more pleasant experience. Let's talk a little bit about what some of these barriers are, like why is developing quantum technology hard? Well, maybe something that's kind of obvious is the actual hardware, the software is challenging. A lot of times people kind of default to thinking about the hardware in this case. But for the purposes of this talk, we're really going to be thinking about pretty much everything but hardware. There's lots of great people who are working on in industry and academia that are working on developing that hardware. But even if I had a device today, I would need actually a way to connect to it and use it. So that's where a new stack comes in. Because quantum computers are like a hardware accelerator, we can kind of cheat off of what we learned from developing for GPUs and kind of draw out this very high-level stack sort of diagram where we have end users working in a very high-level language. We take the programs written there and we compile them down, we transpile them, we optimize them, and then send them off to some sort of cloud service that handles job queuing and management, targeting our programs to specific hardware, and forwarding then everything along to the actual hardware devices with the providers. So pretty much all of this is in common with some of the really specialized GPU resources, except for the part where it's actually running the accelerator that it's running on. So given we're borrowing so much from existing technology and infrastructure, it does kind of come with the same problems. So things like how do we actually integrate new workflows into tools that developers are using, whether that be IDEs or CI/CD pipelines? How do we make reproducible development environments? As a maintainer, that is something I really don't like spending time on, and I really want to make sure that everyone kind of can have access to this my machine. And accordingly, when you start stacking up all of these different layers, it can be kind of challenging to track and debug everything through that stack. And so it either takes a lot of skills and experience or really good tooling to help you kind of track all of that down. So these are some of the challenges on the technology side, but they're honestly kind of familiar. The other main challenge that we face in the quantum tech community is, well, building the community. Obviously, most open source technologies go through the same sort of growing pains. And I think some of the challenges that we have in quantum are that the quantum community is extremely broad. We have folks who are kind of almost on the pure research side. They're mathematicians developing new programming languages. to people in the middle who are developing the cloud infrastructure, that queuing and job management. What does it look like to do CI/CD for a quantum computer? To the folks who are actually building the hardware. And people can come from very widely different backgrounds, very different experience with open source software. And, well, we really want to bring them all together and actually build something together. So some examples of these barriers on a social level are things like hardware access. So sometimes these big compiler tool chains or even just quantum hardware access can be really hard. If you have a really old laptop, it's going to take a long time. So being able to make sure that the community has access to adequate hardware, as you might guess, because this is so closely tied to research, things move pretty fast. And so we really have to be good about not only staying on top of the developments, but packages will break, documentation will be out of date. And so it's really important to kind of keep moving that along, because then that leads to the next problem, which is onboarding. If someone comes to your project and the docs are so wholly out of date, it's going to be really hard for them to get started, even if it's a relatively simple thing that they want to contribute. And lastly, but not leastly, accessibility and inclusion. This is something that I think has been really important to me, learning from the broader open source community and bringing this back to the quantum open source communities is making sure that everyone from all of these widely varied backgrounds and skill levels feels like they can be included, they can learn from each other, and we can build cool stuff together. These are some examples of just kind of the social barriers that we're kind of dealing with in quantum technology. Again, not particularly strange. They're honestly pretty familiar, but challenges nonetheless. So these kind of come together in a community that I want to introduce you to, the Quantum Intermediate Representation Alliance. That is a lot of words and a lot of syllables, but this is a Linux Foundation project under the Joint Development Foundation program, and it is an industry-wide coalition with members like Microsoft, NVIDIA, and hardware providers like Quantinuum and Rigetti, and national research labs like Oak Ridge. And this is really a cool effort that honestly, there isn't really anything quite this broad in quantum tech yet. And the goal is to really help build out this quantum stack, build the tooling and the specifications that we need so that when people are building cool tools, they can actually work together. So that's the full interoperability. And right now, there is a lot of development effort that gets duplicated because you have tool A and tool B. You need to make basically custom connectors between every set of tools. So that's where this intermediate representation comes in. So QIR, or Quantum Intermediate Representation, is LLVM, but make it quantum. So LLVM is a low-level machine representation of regular programs. And so QIR kind of takes that and expands on it to include instructions that quantum devices can also perform. And so if we think about that kind of stack diagram we were looking at before, QIR can really act as the glue between all of these different layers, rather than having to make custom connectors between each piece. QIR is also really interesting because it can represent fully general quantum programs. So that's not only all the quantum instructions that these devices can execute, but all the classical instructions as well, which is really critical to real scalable applications of quantum computing. And because we're based off of LLVM, there's a lot of tools from that tool chain that just work out of the box. As a physicist, I know we like to reinvent the wheel sometimes, but I really appreciate that we can build off the work that others have been working on for a long time and use that to make quantum development easier. Travis Humble is someone who is a member of the QIR Alliance and said that he was very excited for Oak Ridge National Labs, that QIR really provides this kind of focal point for the industry to kind of start converging efforts and actually encourage not only industry applications, but really good research and importantly, reproducible research. So that's kind of a taste of the QIR Alliance and what QIR is. I think it's pretty cool. Hopefully you might think it's cool, but where do we go from there? This is where Codespaces comes in. So The QIR Alliance had been working on developing the specification and started building all of these tools to work with QIR, but it was a really painful experience. There were a lot of, just setting up tool chains that touch all kinds of different languages and frameworks, from Python to Rust to C++ to Julia, it's kind of a mess. So we were really looking for something that we could use to help get people in and get people developing on these tools to kind of bootstrap the effort. We learned about Codespaces and started trying out, and it was awesome. So if you haven't heard about Codespaces, it's a GitHub product that allows you to spin up basically machines on demand from your browser, right from a repo. So you can just kind of, where you would normally click to clone the green button to clone a repo, you now have the option to create a code space, and that then right away in your browser very quickly gives you a VS Code interface to directly work on the code in that repo. So we are now entering the demo zone, and the asterisk or caveat I want to add here is I am working with a lot of QIR Alliance projects, general quantum open source projects as well, and a lot of this is research. I had a really fun time putting together this demo, and it's some of the first times we've actually been able to plug these tools together with QIR. So if it doesn't look quite production, that's by design. And hopefully as you kind of start or explore the quantum development stack, maybe you can help contribute. Let's actually start working on the quantum stack in Codespaces. I'm going to walk you through the entire stack from writing a quantum program in Python. So that would be kind of the experience of either a researcher or user of quantum hardware accelerators. We're going to compile that program to QIR using Python and Rust. Once we have a QIR representation, we can use some C++ tools and LLVM out-of-the-box tools to help optimize it, do things like unused variable cleanup, unrolling loops, things that you kind of expect typically as a part of your compiler passes. And then we'll actually send our QIR program to a cloud provider and actually run it. First things first, I've kind of highlighted in the stack here, we're really working at the very top here, and we'll be using Jupyter notebooks and Python to actually write our quantum program, as well as the Python package Qtip. You can see the GitHub repo for that there. Let's hop over to Codespaces and take a look. All right, so now we're in a local VS Code window here, which I have connected through the GitHub Codespaces extension to a codespace I already spun up, Curly Space Doodle. It's a great name. And you can see I've got 8 cores and 16 gig RAM here, so not a bad machine. So I'm going to take a look here. We've got a Jupyter notebook that I'm going to open up, and there's lots of great stuff in this repo, which you'll get a link to at the end of the talk, but you can learn more about all the stuff that I'm talking about here. But let's actually get started writing a quantum program in Python. So as I mentioned, we'll be using a quantum package called Qtip, and in a very similar way to how you might build up a program, maybe some very early programming classes. We'll make sure we get Qtips now imported. And you can see up here in my notebook, I actually pick the environment or kernel that I'm running my code in. And when I spin up the Codespaces, it actually makes this Conda environment for me called QIR demo. So we've imported our Qtip package here, and we're basically going to build a program here. VS Code is suggesting with the type hinting that I actually insert these type hints, so thank you very much. And we're going to create a program with 3 qubits here. So I will just run this, and you can kind of see that we've got our program, and then we're just adding a bunch of instructions to it. So a lot of these here are quantum instructions. Quantum computers kind of have just like you would do ands and ors or NOT gates on your classical computer, quantum computers also have a bunch of different gates or operations. They have different names, but same sort of concept. So we've got quantum ones, we've got some classical ones here where we're actually reading out memory on our quantum computer. And then we can even do other things like condition some quantum operations on that data we read out earlier. And if we take a look at the state of our program after that, we see basically the same sort of list of instructions. But this then gives us a Python description of a quantum program that we might want to run. The actual program here is a teleportation program, which is very similar to the C move operator. It basically just takes information on one part of your device and moves it somewhere else. So teleportation isn't weird or strange, it's just a move. Cool. Now that we've got our quantum program in Python, let's actually add some Rust to the mix and use Qtip and the PyQIR package to actually compile that Python program to QIR. So we'll go back to our notebook here. And honestly, it's really pretty easy with how Qtip has integrated QIR support. I literally just import this circuit to QIR function. You can read more about it in the docs here, but yeah, I just pass it my program and say whether I want a bitcode type of file out or a text file out. So we'll generate those here. And well, looking at the bitcode isn't super interesting, but if we look at the text representation of it, the file, this is what QIR looks like. Not really designed for humans, but that's okay because it is a machine interchange format. It's an intermediate representation. Sure, we may have to look at it to debug things, but humans aren't meant to be reading this. So what I find really awesome about this kind of approach is Qtip is actually using PyQIR under the hood, if you will, and PyQIR itself does this translation between Python and QIR with Rust. And there's a Rust crate that is ready to go and actually modular, such that if you wanted to write quantum programs in Rust and go back and forth to PyQIR, you could just use QIR lib directly and actually write programs in Rust. And this is actually a really interesting and pretty popular direction recently. So hopefully there are more Rust developers getting excited about quantum. So we've now written our program, compiled it to QIR. Now we get to actually do some of the fun stuff. Actually, it's all fun. But we'll optimize our program with some LLVM tooling and the CAT tool maintained by the QIR Alliance. So if we come back here. So looking at that text file representation of the QIR, again, not super helpful if you want to debug something. So we can actually use, this is the case whether it's LLVM or QIR. So LLVM actually has a nice tool here. It's a command line tool called opt that gives you an optimization pass that actually just takes your program and generates a control flow graph. So I can, in my Python-based notebook, I can actually run bash commands by using this bang here at the front. But I'll just run this command line tool to generate our control flow graph. And I just move it because I don't like the name. And now we've got this kind of text file, but I actually want to see it as it's a representation of an image. So I have an extension installed in VS Code that allows me to preview this. So I will get that maximized here. And yeah, now we have something that kind of is maybe a little bit easier to follow than that giant wall of text. You can see our program has a bunch of kind of quantum instructions at the beginning. Then we had some classical like control flow, ifs, more instructions, and eventually we return to the void. But this is kind of a helpful way if you're just looking to do some quick gut checks or just inspecting what those QIR files are describing. Our codespace also has the image magic tooling installed so that you can also output that directly to an image if you want to share it that way. All right, so we now have kind of a better sense of what our QIR program looks like. Let's optimize it. So I'm going to do the same thing here. CAT is a command line tool written in C++. And as a part of our code space, it actually gets built from source ahead of time and installed where we're working, just so that we don't have to necessarily deal with that when we want to get started kind of working on things quickly. So I'll run this. And the arguments here basically say, all right, we're going to apply some optimizations to our target program here. And all of the kind of settings and configuration for those optimizations are here in this YAML file, the target definition. So yeah, and we can see here we save out to the Qtip optimized program. And we could go through and compare line by line, but kind of a rough high level estimate that I like to look at is just the file size. So obviously the file sizes here are just not that big to start with, but you can see that after we run cat, our file size does go down, and you can see a lot more drastic or interesting examples of this in the actual cat repo on GitHub. So there's lots of cool tests and documentation there that gives you examples that you can really see how drastic some of these optimizations are. Great, so now we have optimized our quantum program. We've got a really great quantum program now, and we want to actually run it. So now we're going to hop back to our notebook and actually send our QIR to Azure Quantum. I'm going to just connect here quick to some of my Azure credentials. Because Codespaces are persistent, I already logged in to Azure earlier, so it actually just remembers that. So I'm just loading those credentials here in my Python session. And I'll go ahead and create a quantum workspace. So now that that's basically like creating the resource on Azure. I will load up the bitcode for, it's a slightly different program than what we generated before, but it's roughly the same thing. And then it's pretty much as easy as just sending this job from input data function. And you can see we've got our bitcode here. We're going to send this to Rigetti, the Rigetti hardware provider, and to their quantum virtual machine target. Sometimes queue times for hardware can be pretty long, so we're doing this to make sure we get it to evaluate quickly. I've now submitted the job. If I want to take a look at maybe some of the details about this job, I can just inspect the details as a dictionary there. And I could print that out, but something I really like about Jupyter Notebooks in VS Code is I can use this variable explorer. And it shows me everything that I've defined in my notebook session so far. And because this is a dictionary, it actually gives me kind of an even nicer way to look at it, which kind of looks like your basic spreadsheet editor. And so if I had a bunch of jobs running at once, I could sort and filter and kind of explore them that way. It works really well for pandas data frames as well. So if you do a lot of pandas stuff, highly recommend you check that out. So let's see if our job is done. And it is. Here's our these were the measured qubit outcomes. So when you measure a qubit, you get a 1 or a 0. And it says here that we ran our program one time. In reality, we should probably run it more than once, but yeah, this ensures that it goes quickly. So now we've actually walked all the way from writing a user-level quantum program all the way down to running it on hardware through a cloud provider. And it really isn't spooky or strange or weird. They're quantum programs, but it's all pretty familiar, and it all can be made really easy in Codespaces. So we've actually been able to walk a quantum program all the way from user space down to running on hardware. I always get super excited about this, and I hope it seems really cool and exciting to you as well. A lot of times people say quantum computing is spooky or strange or hard, but as you can see, we can make it a lot easier with Codespaces. So to kind of wrap things up, Codespaces does make quantum development easier, and it reduces a lot of the barriers and challenges that our community faces. So it allows us to get started coding faster in the cloud. This is great, not only from activating on people's excitement about the topic and getting them contributing to projects, but also making contributing more accessible to folks who maybe don't have adequate computing hardware to actually build the tool chains or compile what they need to. Codespaces also makes it really easy to spin up standardized dev environments. So as someone who's a maintainer for projects, I don't want to spend as much time trying to play, does it work on my machine? And this also makes it easier to deal with some of those rapidly changing research advancements, because we can at least repeatably do what we were doing last week. And on top of all that, I get to work in VS Code, which is definitely my favorite developer tool. It's really popular in the quantum community more broadly, and it's kind of a really nice sort of comfort when you're learning something new and you want to dive in, and now you can actually work in a tool in a space that you are familiar with and hopefully build some cool things. Thank you so much for joining me today, and I hope this might interest you in getting started in developing the quantum open source stack. Definitely say hi to me on the internet. I am crazy for Pi 314 pretty much everywhere, Twitter, GitHub, etc. And if you want to check out the code for this demo, you can go to aka.ms/quantum-codespaces. You can just spin up the code space and get going. And if you're interested in the Jupyter Notebook interface that I was using for the actual demo, they work in a lot of different languages, not only Python, but .NET, R. So definitely check out aka.ms/vscode-notebooks-universe. Thank you so much.